Bueno, no, tiene bien español, en la conferencia va a ser íntegro, tampoco viene de París directamente, viaje, y llegó de ese viaje, nada, no.
Bueno, una charla sin dormir.
Claro. Bueno, es un placer para mí presentar a Ciprian Tudor, a quien conozco desde hace muchísimos años, desde el comienzo del siglo XXI prácticamente, en Samos, en París 1. Ciprian es un gran especialista, uno de los creadores del método de Stein-Malliavin, conjuntamente con Iván de Urbán y con Giovanni Peccati. Ya antes de que se pusiera de moda, ya él me había enseñado algunas cosas en los años 2000, antes de que apareciera el teorema del cuarto momento de Giovanni y David Mara. Entonces, en realidad, el método de Stein-Malliavin es un método muy interesante que tiene que ver con el estado de Miller, pero sobre todo una de las características de Ciprian es que Ciprian siempre tiene en la cabeza las aplicaciones estadísticas, que en general la gente que hace este tipo de problemas, en particular los compañeros que trabajan conmigo, trabajamos más en la probabilidad. Así que yo lo dejo con Ciprian y un placer realmente tenerlo con nosotros.
Muchas gracias, sí. Es un placer para mí también, ¿no? De estar aquí con ustedes, sí. Estoy por la primera vez aquí en Montevideo, sí. No le conozco gente desde muchos años, ¿no? Aproveché una oportunidad de un proyecto conjunto de Francia con América del Sur para visitar a su universidad por la primera vez. Muchas gracias por la posibilidad de hablar aquí. Sí, creo que voy a hablar inglés, porque estoy un poco cansado, no tengo experiencia para hablar en español, pero bueno, si hay preguntas, puedo responder en español. So it will be about this Stein-Malliavin calculus. Time method and in combination with Malliavin calculus. So Chichi explained very well what it is. Okay? It is a method was like 20 years. Okay? So introduced basically by Giovanni Peccati and Iván de Urbán. Okay? So what is the idea? The idea is to measure distances between probabilities, okay, probability laws, and to find the estimates and to apply to the statistics, to limit theorems, and so on. Okay? So I will start with short presentations of method in general. Okay, so what is this? How we do the things? Okay, and then okay, I'll go to, let's say, the option for my recent research, okay, which is a multidimensional time method. Multidimensional, I will explain what it is, not because there is also a multidimensional time method, but here's the proposal is a bit different, okay? And actually, there is a method to quantify the asymptotic independence between sequences of random variables. So I will go to this new method and several applications, okay, several applications of this to various areas. So what is this method? So as I told you, it's a collection of techniques, or probability techniques, to evaluate distance between probability, between two random variables. Imagine you have two random variables, f and g, okay, and you want to measure how far is f from g. No? So this is how far is actually the law of f or the law of g. So this is what we want to quantify, and how to define the distance between the law of f and the law of g. Usually, the general definition for the distance is this kind. Okay, supremo, take the supremo for expectation hf minus expectation hg, or h, the function h belongs to a class. Okay, and in general, it's a large enough class of functions, and depending on what you choose this class, you have various distances. Okay, so I think I put here some examples. Okay, for example, if you took the class of function h to be the class of Lipschitz continuous function with the Lipschitz norm less than 1, so you get the Wasserstein distance. Okay, so another Another example is the Kolmogorov distance. So you obtain the Kolmogorov distance when you take the class of function to be indicator function, okay? Indicator function meaning this class, okay? Indicator function I'm receiving this z, where z is moving on the linear line, okay? So this defines the Kolmogorov distance, which well known, okay? It's defined in this way, okay? But there are other distances you can quantify, okay? Total variation and so on, so on. Okay, so this is the purpose of the Stein methodology to look to the distance between two random variables to try to find the estimate, okay, inegalities, bounds, okay, for this distance. Okay, well, of course, you imagine a particular case of interest is one of these two random variables. One of these two random variables is Gaussian, okay, because I mean you have always something which is asymptotically normal, for example, in Lille theorems, okay? You want to quantify, okay, to measure what is the distance, okay? How to evaluate the distance, okay? And because there are a lot of applications of this approximation in Lille theorems and statistics, okay? And so this is the main object, okay? You have a random variables arbitrary, let's say, and you have another one which is Gaussian, okay, and to measure the distance, okay. So this I mean the main interest is here, okay. But you can also choose another target distribution, not Gaussian, okay. So there works dealing with other distribution like gamma distribution, Poisson class, okay, and so on, okay. And actually, the method, same method is very old method, okay. It's a long tradition, decades, okay. What is new? Let's say new is a combination of this with Malliavin calculus. So I will arrive to this too. Okay? And, well, what is the idea? So now I discuss the time method for the normal approximation, meaning that I want to approximate the normal distribution by another random variable. Okay, so the starting point of the method is this characterization of the normal distribution. Okay, and the result is the following. Okay, if you have a random variable z, which is Gaussian, okay, with zero mean and the variance sigma squared. Okay, so z follows this distribution if and only if you have this identity. Okay, sigma squared expectation of f prime z minus expectation of z is zero for a large class of functions, determinate function f. Okay, so this is what you can prove by hand. Okay, and okay, so there are two directions. Okay, if z is Gaussian, you have this identity. Okay? Just to use, let's say, the density of the normal distribution and some integration by parts and negatives, but you have also the converged direction. So if this is zero for a large enough class of functions, then you have z must be Gaussian with zero mean and expectation sigma squared. Okay, and well, this is well known. Okay, and everything starts from here. Okay, and then you have an intuition. You have another random variable x, okay, and you want to think how far is this random variable from the Gaussian, okay? So you look at this quantity, okay? This quantity is zero if it's Gaussian, but you may think, okay, if x is close to Gaussian, okay, this quantity should be close to zero, okay? So this idea, the first point where the time method start, I think, okay, and from this observation, I mean, the theory expanded, okay, so they are leading to various bounds, okay, and so on, okay, and well, you also, in the Stein method, you also have also Stein equation, okay. This is the Stein equation, so here everything is determinist, okay, and you recognize here is the left-hand side the quantity from before, okay? So if you put here z Gaussian and you take the expectation, this is zero, okay? And okay, so in this equation, the function h is given, okay? And you have to find f, okay? You have to find f. And this is very important, okay? It's not a very difficult equation, but I mean, it's very important for the method, okay? So the idea, we look to this equation, okay? And the idea is to try to solve, okay? You solve the equation, you find the solution, okay? You find the solution f which depends on h. Okay? For every h, you have a solution f depending on h. Okay? And you need to look to the solution. I mean, to prove that the solution is nice. Nice, I mean here bounded, okay, with differentiable with bounded derivatives. Okay, and in this case you can prove it. You can prove it. Okay, you can prove that you can solve this equation. There is a unique bounded solution, which is nice. Okay, well, what you do next? Next, you will replace small x by a random variable capital X, okay, and you take the expectation in both sides, okay. You put here capital X, and you take the expectation in both sides. So what you obtain is the left hand side you have this, and this is the right hand side, okay. And now you know this is the distance. If you take the supremum here over h, this is exactly the distance between the law of f and the law of z, okay? And but what the people do is they say instead of taking the supremum here, okay, I will take the supremum here, okay? I will not compute the left hand side, I will compute the right hand side, okay? And well, the right hand side is this one, right? And here the idea is that you can do some integration by parts. Okay, so this is a place where the Malliavin calculus enters into the plane. Okay, so how you do the integration by parts? You look to this term. Okay, so if you look to this term, okay, there is a well-known formula in Malliavin calculus. In this formula, when you take the expectation, you have f prime coming here times another guy. Okay, this other guy is specific from Malliavin calculus. Okay, I will not enter into details. Okay, you have operators from Malliavin calculus. You have these Malliavin derivatives. L is also one of operator. So I mean, if you know, you know. Otherwise, I mean, we can find in the book and Picati and so on. But the idea is. This is, I mean, the main idea from Nudana Picati. This integration by parts, okay? If you do the integration by parts, okay, you can put x prime in factor. So x prime will be in both terms here, okay? And you do this, okay? So what you obtain when you take the supremum, so basically this is a distance between f and z, okay? You don't take the supremum here, you take the supremum here. You apply the integration by parts. You put x prime in factor. And you have f prime multiplied by sigma square minus this quantity, okay? Augmented quantity, okay, in principle. And now at this point, you remember that f prime h is the solution to the Stein equation. And you remember that the solution is nice, okay? It's bounded to the bound derivatives, okay? And you just bound the derivative by a constant, okay? This is a constant, okay? And you find the bound, okay? So the distance between the law of f and the law of z will be bounded by exactly this quantity, okay? And so this is a main Stein-Malliavin bound, okay? So if you are able to compute this, okay, you have bounds for the distance between the law of f and the law of z, okay? And I mean, simple inequality finally has many applications, okay? So when you work on linear chaos or functional to the Brownian motion, you can compute it. In many examples, you compute it explicitly. And in many situations, also the bounds are pretty sharp. Okay, you can do that; they are pretty sharp. And well, anyway, what we can also notice that at the end, there is no supreme here. Okay, just a constant. Okay, and everything depends on f. You random variables f. Okay, and you have a random variables f. You compute this quantity, and you have a bound from the distance between f and the normal distribution. Okay, well. So this is the story, okay? It's a story by Newton and Picati and so on, okay? And well, so now I'm going to my point, okay? What I want to explain is an extension of this method, okay? So actually, this comes from work by Leandro Pimentel, okay? It's a guy from Rio, okay? So he's not a guy from my community, Malliavin calculus and so on, but he's doing KPZ equation and other things. But I had the opportunity to to follow taught by him in Brazil few years ago. So, and yeah, he worked on something similar, actually. Okay. So what he did? Okay. So you have a random variable x, which is arbitrary, and y is a random vector also arbitrary. Okay. So for him, the purpose was to look to the distance between this probability distribution. Okay. So first is the law of x, y, okay? So y could be multidimensional, but imagine it's equal to 1. So you have a arbitrary couple to whatever x, y in this case, okay? And you want to measure the distance between this couple, x, y, and the distance is the probability of pz times py. So this is a distribution of a couple z, y. Z is Gaussian, y is arbitrary, but both are independent. Okay, so he was interested in this, but for other stuff. Okay, it was a composite problem. Okay, something which is Gaussian at the beginning and evolves and so on. Okay, but well, so how to do this? You know, now the target is not Gaussian. No, it's Gaussian, and the second component is arbitrary. It can be anything. Okay, and well, and I mean, the story here is pretty similar with what happens in the classical Stein method. What I explained until now. Okay, so you also have some operator. Okay, I denoted by NF. Okay, which is very similar with what I wrote before. Okay, so is sigma square, which appeared before, is derivative with respect to x of f and minus x f x y. Okay. Now f is defined on r power b plus 1. Okay. So that means x is real, y is rt. Okay. And so what is new here is I have exactly the same expression, but y appears. Okay. This y variable appears here. Okay. And you also can characterize the law of a couple Gaussian arbitrary. Okay, first component is Gaussian, second component is arbitrary, but both are independent. Okay, so the first observation is this one. Assume x is Gaussian. Okay, and x is independent of y. Then, if you take this operator, okay, and you take the expectation, okay, you apply to x, y, take the expectation, it is 0. Okay, so but you will see that it will be if and only if zero. Okay, so to prove that this is 0, I mean it's also classical proof. So you just use the classical Stein method. Okay, you have the classic x is Gaussian. Okay, remember that x is Gaussian. Okay, so you have this characterization of the normal distribution, right? For each y, y inverse t, you have this characterization. Okay, you write as an integral. Okay. And now remember that x is independent of capital Y, okay? So you can integrate once again with respect to dpy, okay? And if you integrate with respect to dpy, using the independence between x and y, okay, you find this equality, okay? But what is nice is that you have so this is both sides are are calculated. But what is nice is that you have a converged direction, okay? So you have this operator n, okay? And you suppose that the expectation of n f x y is 0 for a large class of function f, okay? Large class for me would be function with bounded partial derivatives here, okay? And if this is 0 for many functions f, okay, you can prove that x is Gaussian and x is independent of y, okay? So this is pretty strong, but the proof is easy, okay? The proof is easy. Just to look to the characteristic function, for example. So maybe I put here something. So you look to the characterization function of the couple x, y, okay? This is the definition, you know very well, okay? And then you take the derivatives, you look for the PDEs satisfied by the characteristic, okay? And you take the derivative with respect to lambda 1, okay? So for lambda, you arrive at something, you apply So you apply the style identity and so on, okay? And you find at the end that this characteristic function of the couple will be the characteristic function of y times something which is the characteristic function of the normal distribution. And from this equality, you can deduce that x is quotient, okay? And x is the level of one. So, well, so you have this characterization. So then when I understood this, I also understood that we can do the same as for the classical time method, okay? So you have a characterization of this law. Remember, this law is not quotient, so it's just a couple of quotients, the first component, arbitrary, the second component, and the components are independent, okay? And you try to do the same as in the classical time method, okay? So you define an equation, so it's the same equation as before, but we have this y in addition, okay? And so h is given, you have to find f, okay, which satisfies this, okay? And you can also manage to prove that this equation emits a solution. Actually, the formulation is a unit boundary solution, okay? And this solution is also nice, okay? So I put here, I will put now the property to the solution. You have also, actually, you have an expression of the solution. This will be the solution. It's something, okay? But concrete, okay? You have this, okay? And what you can prove? You can prove that the solution is bounded, okay? You have some bounds. You have the bounds for the derivative with respect to x variable, okay? But what is also important is this last other mu, okay? You have to deal also with the derivative with respect to the y variable, okay? So basically, the first two inequalities comes from the classical method, but this last inequality you have to prove it, okay? And well, so once you have this, okay, you have the Stein equation, you have the solution, you can control the solution. You try to do more, okay? So the idea will be here to measure the distance between this distribution, x, y, both are arbitrary, and this limit distribution, z, y, okay, where the components are independent and so on, okay? So the distance will be this difference, okay? You take the supremum here, okay? And you say exactly what you said before for the classical Stein method. I will not compute the supremum here, I will compute this guy, okay? Because here I can do an integration by parts, okay? So I will do the integration by parts here, okay? I will do the integration by parts, but what happens when you do the integration by parts, okay? So here imagine you have f prime, but you have the derivatives of f also. What is new here that you have the derivatives of x, but also the derivatives of y, okay? So at the end, okay, when you apply the integration by parts, okay, for example, for this term, okay, just to say that you have something dx, so d minus a minus 1 is like dx in general, okay? Don't matter. But you have something new, okay? You have something new, which is a scalar product between a derivative of x and derivative of y. So this is a new guy appearing here. And now you remember that as the derivatives are bounded, okay, you bound the derivative by a constant. I know that the derivative with respect to x, bound derivative with y is bounded, and I will find an inequality, okay? So the estimate will be this one, okay? So for a technical reason, I will work here for with the versatile distance, okay? So it will be the versatile distance because of some approximation argument, okay? Because I can solve the Stein method for some functions which are bounded with bound derivatives and so on. And then I can approximate the Cauchy function by this class of function, okay? But what is the distance? The distance between my two distribution, okay, will be two terms, okay? Will be bounded by two terms. The first is exactly the one coming from the standard Stein method, okay? So the first term here is something that measures, evaluates the distance between the log x and the Gaussian distribution of z, okay? So it's exactly the last one. But you have a new one, okay? New one, which is basically derivative of x and derivative of y. And this new guy, okay, what it measures? It measures basically the decorrelation, okay? the correlation between X and Y, because at the beginning the components are not independent, but in the limit they are independent, okay? So this second term, okay, is something which quantifies the correlation between X and Y, okay? Well, and so this is a multidimensional method of assessment.
But sorry, these are centered, these operators in centered random variables. These
They are-
lines, for instance,
Which one? This is not centered, for example.
not centered.
No, no. And
In the second line, in the below, in the second line,
this is not centered, no.
because you said the correlation.
The dependence, they say.
Okay.
The dependence.
And question, if X and Y are independent, this gives zero.
If X and Y are independent, this should be zero, yes. You can take it,
Okay.
yes. Yes. Okay. Well, so this is this variant of the Stein methodology. We allows to quantify the asymptotic independence. So what is this asymptotic independence? Imagine you have two sequences of random variables, X and Y n, okay? And if you apply this method, you can compute, okay? You can compute the following distance. The distance between X and Y n, okay? It's a couple of, let's say, arbitrary sequences, okay? And a limit distribution z y n, okay, for example, okay? The method allows to quantify this. And imagine this converges to zero, okay? If this converges to zero, this means that when n is large, okay, you have some non-dependence at infinity, you know, that I mean, the law of xn and yn becomes independent at infinity, okay, if this converges to zero. So people call this in general asymptotic independence between xn and yn, okay, and can quantify this by this method, okay, and so it's exactly what I said. When this distance goes to zero, okay, you can conclude that these sequences are asymptotically independent, okay, meaning that basically the distribution of the vector is approximately the product of marginals, okay, and well. So we have some application of this method to some estimators, to limit theorems, to random matrices, and so on. Okay, and if I have time, I will explain for the stochastic heat equation. And but I think I will start with another example. Okay, and another example. Meaning what happens on binary chaos? Okay, because this method was general. Okay, I have my random variables were arbitrary. Arbitrary, I mean, we have to have some regularity, okay, to differentiate in the Malliavin sense, this kind of things. Okay? But anyway, arbitrary. But now what happens if the sequence belongs to a binary chaos? Okay, binary chaos, you know, or you don't know, but and well. An element of the binary chaos is a multiple integral, okay? This is a notation EPFK. So f is a function, fk is a function of p variables, okay? And if you want to understand somehow basically, you integrate this f with respect to the volume function p times, okay? So this is a multiple integral, okay? It's also an element, a generic element of the binary chaos, okay? So, and well, you have some isometry of multiple integrals. So, for example, if you have two multiple integrals of different order, z scalar product is zero, okay? For the L2 norm, you have some formula, okay? And isometry formula and so on. And well, actually, this method gives something interesting with the binary chaos, okay? And so, for example, you have a sequence that compares to the normal distribution, okay? So, as Chichi explained at the beginning, we have theorems, famous theorems, formula theorem for this to characterize or say when a sequence of multiple integrals in binary chaos compares to the normal distribution. This is so famous formula theorem by Norat and Pecati. Okay, and but what happens here? I take another sequence. This is arbitrary, and the limit is arbitrary. Okay, so you have a limit of this in some sense. I will not be very precise. For example, L2 because it's a strong limit. Okay, So if you have one convex to the normal, another one which is arbitrarily convex to something else, okay, you want to ask what happens to the couple when you have the joint distribution of east k, y k, okay, and you assume that you have no correlations infinity, okay, so the expectation of the product goes to zero, okay, and actually you can prove that if you have at the beginning you have no correlation, this will give you asymptotic independence actually. So if east k goes to Gaussian and east k is in linear chaos and yk goes to something else, then automatically the couple converge to a vector. Vector. First, this is Gaussian, this is arbitrary, and the components are independent. Okay? For example, here this is this method and some other technical results allow us to obtain results like this. Okay? And well, and you also have the estimate for the distances with this Malliavin operator. So let me give you maybe an example. I don't know if two, maybe two more. Okay? And well, so what can you do? You have an example of sequences where the first component is Gaussian, the other one is something else. Okay, and in this case, you can find estimates for the distance and so on. For example, I go to a very classical example, which is Breuer-Major theorem. Okay, so you have a fractional variable motion here. Okay, fractional variable motion pH, and you take the fractional noise, which is this difference. Okay, and you apply a Hermite polynomial. HK is the Hermite polynomial of order Q. Okay, and well, this is well studied. Okay, so we know how to analyze this sequence. Okay, so for example, if Q is equal to 2, this will be the square minus 1. Okay, so this if Q is equal to 1, then you will have a quadratic function of the fractional variable motion. Okay, and so you know the conversion of this. So depending on H, this will converge sometimes to Gaussian, sometimes to something else. Something else is this Hermite process or Rosenblatt if Q is equal to Rosenblatt distribution and so on. Okay, and well, so for example, if H is this interval, okay, you normalize the sequence by 1 over square root of n, and you know that this goes to a Gaussian distribution with HPT value. Okay, so this is all stuff. Breuer, Major, Tucker, and so on, and many others. Okay, and well, and also here, if you want to estimate the distance versus kind of variations between Vn and the Gaussian limit, you know how to do it with this time method. So this is in a book by Notaro Pecati, for example. So you have other distance. Okay, and well, but what happens if H is not in this interval? Okay, it's close to 1. Okay, if H is close to 1, then with a different normalization, this will converge to this non-Gaussian distribution, Rosenblatt here or something. Okay, and well, for example, this I take here Q is equal to 2. Okay, you see that this will be a quadratic function of fractional variable motion, and you have another normalization, and you know that for H, for example, between 2 over 4 and 1, this will converge to something which is like this. Okay, constant times L, or L is a Rosenblatt random variables. It's called Rosenblatt random variables. Okay, well, and also you can estimate the distance between this and the limit distribution. They are methods. Okay, they are methods are criteria to estimate the distance. But what my method permits to do is to look to the joint couple. Okay, so the first is Gaussian. You put Vn, which is Gaussian. You put Un, which is non-Gaussian. Okay, for each one you have the distances, but you look to the distance between the couples. Okay, the couple, the first couple is Vn, Yn, and the couple Gaussian Rosenblatt. Okay, and so actually exactly what I said. Okay, Vn, Yn. You can deduce that you have the convergence to something. Or first is Gaussian, the second is Rosenblatt. Okay, both are independent. Okay, and And you can also quantify this. So how you quantify when you, if you are in the good range, okay, so you have to put H in the good interval.
Even if VM and UM are constructed from the same.
Exactly. Even
This is the main property that Ciprian didn't say, but this is the main property of the count of fact in that the limit has an heritage of the independence between the correlation zero to count transform in independence.
yes. No, that's true. Yes.
This is
Because
They are
also
constructed.
an arbitrary chaos.
They are constructed from the same structural variables, for example. Yes. Yes. One corresponds to the Gaussian, another to Roosevelt, as the limits are independent. Yes. Asymptotic indefinite. Yes.
This is it's a new result, Ciprian.
Yes. Yeah. And well, you can deduce this, okay?
But you have converses in different chaos, in different orders. You take P12 to VL also.
You have some conditions, this condition, for example, yes.
But larger than 3, for Q equal 2 is the same object. Because it's
Yeah, because you have
second order polynomial, then.
Yeah, exactly, yes.
Okay.
Yeah.
Yes.
And what you quantify, so when you quantify, okay, you just apply the theorem, okay, and you have something, okay, so I wrote this to see, but I don't know if I put some or no. You have something, but what is important is to estimate the Malliavin derivative of Vn and Malliavin derivative of Un. So this is a new guy which you have to compute, because for each component you have the distances, okay, just you need to see how the dependence is quantified, so.
Because, sorry for asking again, because you have a priori, you have no correlation because you are in different.
Yes. See, you need to have no correlation.
No correlation.
Yes. Even if you are in the same cause and you can have some no correlation, no? If asymptotic correlation. So if you have this transforms in the truth.
But one is Q equal to 2 and the other is class.
Yes, it is. So another. So because I have 10 minutes, okay, I will explain you another application of this, okay? So what we try to do in the okay? So you have some estimation problem in some SDEs, SPDEs, for example, okay? And well, this is an example of the heat equation, okay? So you have the heat equation of semi-linear, because you have component here, P, which is non-linearly feasible, but well, so these are technicalities, but I want to explain you the idea more than technicalities, okay? So you have an estimation problem, okay? You have heat equation and you have drift parameter theta. You want to estimate, okay? So this is not a problem to estimate the drift parameter in SDEs, SPDEs, okay? And there are methods, okay? Many kind of methods, okay? And the one is based on the variation of the solution, okay? So I said that the noise, the space-time wave noise. So basically, space-time wave noise is like a Brownian sheet, okay? And there B, it has to be globally wave sheets, okay? And the solution, it understood is a Miles-Lens. Miles-Lens meaning that you have this integral equation, okay? And U solves this, okay? So if you look to this solution, okay, you have a first part which is wash integral, okay? Wash integral of some Gaussian kernel respect to the noise, okay? So this is actually a real integral with respect to the sheet, okay? With respect to the Brownian sheet. It's the integral is deterministic, okay? And you have another term which is you have the so-called kernel here and B appears here, okay? So this is the solution. But you know that I mean about the results, property of the solution, this all stuff. We know many things, okay? Not to mind. We did this, okay? Comes from the land and so on, Martha Sands. So you know that you have a unique solution and you have estimates for the moment, okay, for example, the moment of finding and so on. Well, and my problem is to estimate the drift parameter theta, okay, you have a drift parameter theta, and there is a method based on the variation, power variation of the solution. So you can consider power variation. The solution has two parameters, time and space, t and e, okay? You can take variation with respect to time, okay? Meaning what? You take the difference in time here and you fix the x, but you can also do variation with respect to the space, okay? And when you look to this sequence, okay? So this is observation with x, okay? You observe the solution at some discrete times and at any spatial point, okay? And you consider this quartic variation, and this is also well known that you have a limit of this, okay? You have a limit of this, and in the limit, okay, the parameter theta appears, okay? And if you want to estimate theta, how to estimate? You just take a Vn 6 divided by P5 times Vn, okay? So this quartic variation gives you an estimator for the parameter theta, okay? Well, good. And you also know that you have this kind of generalization theorem, okay? If you take the quartic variation and you subtract the limit and normalize by square root of L, this will go to a normal distribution.
This is obtained via a very major multidimensional.
Via classical time method, for example, you can do it. Yeah. Yeah. And you can also find the distance, for example. Okay. And okay, so this will be the estimator, okay? So if Vn converges in Vn converges actually around sure in L2, for example, but the estimator will converge at least in probability, okay? And you also can put a general limit theorem for the estimator, something like this. You also have a Gaussian limit, okay? And with some known variance. Well, and but the idea how to apply my method here is to look to some asymptotic returns, okay? So you have an estimator, okay? The estimator is constructed in terms of the observation, okay? The observation as these guys, okay? These are the observation. So the estimator is defined in terms of this, okay? And well, imagine that you take a part of the observation, okay? A part of the observation meaning that you take UTX, okay, where I belongs to an interval which is which has a cardinal Gn, okay, the cardinal Gn is Mn, okay, which is between one observation and n is the maximum observation, okay, because of the maximum at n here, okay, and okay, so you take a part of the data, okay, so this is partially the data. So the question I ask is how this part of the data affects the whole estimator, okay? And so how much data, how many data can I keep in the estimator? Can I keep to not affect the estimator and so on, okay? And so a method to do it, okay? So I mean, you can have is the data, you can have other data, for example, Gn is 1 to n, you can have only a part of the data when you have a strict inequality here. And for example, a part of the data, if you take, for example, n to power gamma data, when gamma is strictly less than 1. In this case, you have a part of the data, okay, and so on. And what we do, we want to compare. Okay, so this is the estimator, okay, the asymptotic distribution estimator, this is the data, okay, and you compare, you know that the asymptotic distribution of the estimator is Gaussian, okay? And you compare it to distribution, okay? And if the distance between these two guys will go to 0, what I deduce? I deduce as an estimator, the asymptotic distribution as an estimator, is asymptotically independent of the data, okay? And meaning that if you have asymptotic independence, the data here does not affect too much somehow. Let's say the extreme values of the data that not affect too much the estimator and so on. So these kind of problems we try to solve, okay, to understand, and so finally, so So the estimator is basically the quantification. So this is the asymptotic distribution of the quantification. And we look to this, okay? And we look to this to distribution and we compare. So let me just go to the conclusion, okay? So I look only to the linear case. We can extend to the same linear case, so B is 0 here. But let's start to the linear case, okay, to see what happens. So I know things about the solution. In this case, it's Gaussian, okay, and it's Gaussian. You know the covariance of the solution, and you have this quantification which converges to this quantity, and I look to the renormalization of the quantification as total the limit and normalize. I know that this distance, this goes to Gaussian, and the distance between this and the Gaussian is something like constant multiplied by 1 over square root of n, okay? And well, so this to estimate the distance here, you apply the standard one method, standard manual calculus, okay? And you find 1 over square root of n. But now I go to the multidimensional, okay? So remember my formula. If I have a couple, I want to compare the distribution with the z, y, for both are independent, okay? So remember that you have two terms. So the first is what we obtain for the classical method, and the second one is the new guy, okay? That measures the dependence between x and y, okay? So I apply this to the estimator and the data, okay? So
Sorry, Ciprian, but in the estimate, you use the same data that is on y, or you separate an estimate with one and consider the other in the y? I didn't understand that. You estimate with all the data,
you estimate with all the data, okay?
so in the y, there is the data that is used in the estimation,
Part of it.
a part of it.
A part of it, exactly, but a part of it.
Okay.
Yes. So, well, yes, this we have other data here. Here you have a part of the data, okay? And you measure the distances. And if you apply the method, you find something like this, okay? So I have an estimate, it's a constant, mn divided by n to power 100, okay? So mn is how many data are here, how many data are here, okay? So imagine that you have all the data, no? If you have all the data, mn is equal to n. So this will not converge to 0, so you will not have asymptotic independence, meaning that if it's something which intuitively you accept, no? But if you have an estimator and all the data, this will be not independent, no, asymptotically, because all the data affect the estimator, no? But if you have only a part, okay, so for example, if you have here mn over n goes to 0, for example, mn is n to some power gamma, with gamma 6 less than 1, this you have some asymptotic independence. So this is another example where you can apply this method, okay?
But it's natural because you take a square root of n, finally, when n is large, it's a small number. So,
Yeah.
but if you take n over 2, then
If you take what?
n over 2,
Power 2, yes.
then it remains, I mean.
A remains, yes, it's not yes, yes.
But that is, I suppose that we can also think about the bootstrap in the second part, because we have asymptotically independence. You can simulate, given the part that you didn't consider in the first part, and then you can make a lot of bootstrap in the second part to obtain and fix a joint distribution and a joint independent distribution. Asymptotic. I suppose that it can be made.
So this okay, so this was the idea. Yeah, I wanted just to give you some examples of this method applies, okay? what to do with this method and so on. Okay? So these are now there's the estimate. Okay, so you just need to estimate. It depends on the covariance of solution and so on. So these are only calculation, but I think I will not insist here. You know, there are some.
You use the linear chaos to compute the derivatives.
Yeah, because because the solution is Gaussian for the moment. So I have the solution to power 4 law. This is a linear chaos expansion. And then we use yes. And then to extend to semi-linear, you use other tricks. But for the linear, yes. But then this is for the linear because other guy is more regular. Yeah. So this is basically.
Another question, sorry for bothering that much. In this problem with the theta, do you have a Girsanov theorem to estimate the,
No, the sum works for the SDX, but not for SPTs, as far as I know. I know that for SDX, you can use the sum to estimate this and so on, but for SPTs.
the question is if for different values of theta, you have equivalent laws.
Yes.
And if you can express the density by some, I don't
This
know.
that's what we do for SDX, yes.
Yes,
But,
this is what.
here, yeah, I think here is more complicated.
No, it's not complicated.
I don't know how, but it's not used yet. Yes. I don't know the details.
Two-dimensional parameters in
Space-time.
space-time, the Girsanov is not explicit as exponential, but
There is some.
Xavier Young made some a long time ago, Girsanov for this type of Gaussian integral, but this is not a explicit formula as Girsanov in one-dimensional parameter case. And then
Yeah, never used for SPTs actually.
No, there is also some formulas for Gaussian processes with the, I don't know, eigenvalues of something. By
yes,
side.
in this case, B equals 0.
Yes,
Maybe for beats it was different. Yeah.
but even you can, if you are lucky enough, you can use it for B equals 0 and B different from 0. No, only curious.
Hay una pregunta de Diego en el Zoom. Diego.
Hi. Thanks for the nice talk. Yeah, my question was about the assumption that in the general model that X is univariate. Is that important? Can it be generalized to the multivariate case?
Yes, we have I did not explain here, but it is possible. We have a work, okay? We have a work where we did this multidimensional. This can be multidimensional, yes. Yes, we have also a bound which extends the classical one, yes. I can give you the reference on that. But,
and what does it change there? Is it more?
What happens for the general? For the general estimates, let me go to.
So instead of the ODE that gives you.
Here instead the first term is changing. Okay, so you have here a sum of joint derivatives here minus the covariance matrix and so on. It's exactly what we have in the class.
A double sum on H and G.
Double sum, yes, double sum of X and G. Okay, you have the covariance matrix is C and G. Here you have the joint of matrices. But these terms appear in the classical method. Okay? It's a paper by Newton Peccati de Bear.
Ciprian Peccati. For vectorial.
Yes, that's correct.
For random vector.
But there is, yeah, it is possible. Yeah.
I see.
Okay, thanks.
because I have to use the result for multidimensional.
Yo no soy.
No prometo.
No,
que venga
lo que coordinanza. Ti impone.
Moi, je dis que, en fait,
Perdón, no,
ton article,
Nos vemos, Diego. Nos vemos, Maine.